In this presentation, I will provide an easily understood explanation of how a histogram is formed and present an example of how a histogram might be used in image formation and analysis. If you're unfamiliar with how shades of gray are displayed on a radiographic image, you might want to view my Data Behind the Pixel in Radiology presentation. If you search for histogram on the web, you'll find that frequency distribution is often mentioned. What is a frequency distribution? How is frequency distribution calculated? And why should I care? To begin, let's take a minute to review what a pixel is and a pixel's role in radiography. All radiographic images are comprised of very small dots called pixels. See on this magnified image how the image becomes blocky and blurry. This blocky appearance are the pixels becoming visible by magnification. On most radiographs, the pixel can be one of 4,096 shades of gray, ranging from black to white. Most manufacturers specify pixel size in terms of pixel pitch, measured in micrometers. This grid represents a pixel array of a digital imaging plate. The manufacturer of this particular plate specifies their plate has a pixel pitch of 125 micrometers, which means each pixel is 125 thousandths of a meter in size. To translate the measurement into units that are more easily understood, do the following. First, convert micrometers to millimeters. Divide 125 micrometers by 1,000, and your answer becomes 0.125 millimeters. Now divide 1 pixel by 0.125 millimeters, and you will derive the answer of 8 pixels per millimeter. In radiography, resolution is normally expressed in line pairs per millimeter and measured using a resolution grid. The larger this number, the finer the resolving ability of the imaging system. It is understood that a line should span at least 2 pixels to be reliably demonstrated on a digital radiograph. This means that an 8 pixel per millimeter image will demonstrate details down to about 4 line pairs per millimeter using radiographic terminology. Most imaging plates range from 3 to 10 pixels per millimeter. To demonstrate very small structures, the pixels must be different densities. To possess characteristic we call contrast, and this is where histograms come in. The histogram is a quantification of all the density values on a single image. I know I said this would be easy to understand. Please bear with me. Earlier, I stated that a radiographic pixel normally displays a minimum of 4,096 different shades of gray. This means that a plate devotes 12 memory locations to store the pixel's density information. Remember that a memory cell can contain either a 1 or a 0. Let's suppose we use a simplified plate that devotes 2 bits per pixel, or 2 memory locations per pixel. This would mean that each pixel could be one of 4 shades of gray. 4 values are much easier to keep track of than our 4,096. Here is our simplified imaging plate with some of the pixels filled in. For this example, this would mean that a pixel with a 2-bit memory location containing 2 zeros would display as black, black being no light projected through the pixel. A pixel with the memory locations containing a 0 and a 1 would display as dark gray. A pixel whose memory bits contain 1 and a 0 would display as light gray. And finally, a pixel with 1 in both memory locations will display as white. This accounts for all 4 possibilities for any pixel in our simplified imaging system. How about we radiograph an AP hip using our simplified imaging plate? Don't forget that any pixel can be one of 4 shades of gray. To keep things simple, the pixels on this plate will be large, each pixel about 25 millimeters in size, which translates to about 10 pixels across and 11 pixels down to cover the entire image of the hip, for a grand total of 110 pixels in the image, a much easier quantity to keep track of than the 4 million, which is the approximate number of pixels in a conventional hip image. If I fade the outline of the hip, with some imagination you can see this is indeed a hip image, but with very low resolution and limited dynamic range, or few shades of gray. To begin our histogram analysis, we need to count the number of pixels with a particular density value. Let's start by counting pixels whose 2 memory locations contain a 0 value, or pixels displayed as black. Note that there are 26 that meet this criterion. From there, now count the pixels containing a 0 and a 1, or a digital value of 1. These pixels are typically covered with soft tissue and are displayed as dark gray. Note that there are 37 dark gray pixels. Pixels that are partially covered or very nearly covered with bone are assigned a binary value of 1, 0, which is a digital value of 2. These pixels are assigned a light gray color, and there are 18 of them. Finally, there are pixels mostly covered with bone, and these pixels are assigned a binary value of 1, 1, which is 3 using digital numbers. And the computer determines that there are 23 pixels that meet this standard. All the pixels are now counted, and we are ready to generate a histogram of the image. To begin, let's draw a background to display our data. Most histograms I've seen omit this step. Now let's draw a black bar of 26 units high, and a dark gray bar 37 units high, and a light gray bar of 18 units high, and finally a white bar that is 23 units high. At this point you're scratching your head and saying, well, this is just a bar graph. And you would be right. The histogram is a bar graph containing a minimum of 4,096 very thin bars, all displayed in a couple inches of space, so the result doesn't look like a bar graph. Also, some histograms, the bars are all displayed as one color, so they are not distinct one from another. So the process to produce a histogram is to sort the density value of the pixels, count the number of pixels with the same density value, and display the result as a bar graph. To make this point abundantly clear, let's compare my example to some real-world values. My example pixel grid was made of 10 by 11 pixels. A real-world hip is captured by a 10 by 12 image, which would include a rectangular matrix of about 2023 by 2438 pixels in size, assuming 8 pixels per millimeter. My example grid contained a total of 110 pixels. A real-world 10 by 12 image would be made of about 4,954,828 pixels. A large number for you and me, but not a large number for a computer to analyze and display. The grayscale for my example pixel plate was set to 2 bits per pixel, or 4 shades of gray. On the other hand, a real plate would display 12 bits per pixel or more. 12 bits works out to 4,096 shades of gray. So, how are histograms used in radiographic imaging? Finding where an image is on an imaging plate is the first thing. Often, especially for DR imaging plates, a small part of anatomy is imaged using a large plate, such as a finger image on a 14 by 17 imaging plate. A PA projection of adult finger needs only 2" by 5" field at most. This means that 96% of the plate's pixels go unused. If the radiograph were restricted to pixels used to capture the finger's image, file size would be reduced by that amount. Just envision how a PA finger would appear if displayed in a 14 by 17" frame. Most DR and CR systems automatically mask images. This provides a black border around the collimator margin. Getting rid of the large white border surrounding the smaller images will reduce eye strain for the radiologist. DR and CR radiography systems record a much larger span of densities than did film screen imaging systems. To display all these densities using a single image would produce an unacceptable result that would appear gray, flat, and washed out. Some systems use a histogram to aid in correcting contrast and density levels. DR systems may momentarily display an uncorrected image before correction algorithms are applied. Finally, the histogram may be used to evaluate the image relative to the exposure factors used. In today's world, it is difficult to produce an overexposed radiograph. Systems take too dark pixels and can correct them to proper levels. The only indication that a radiographer has that an overexposure has occurred is that the S number, the LGM, or exposure index is out of range. Some of these values may be derived from analysis of the histogram combined with other mathematical characteristics of the image. From this point on, the information I am presenting about image formation is my observation and opinion regarding how digital systems process data. I have worked with film screen, CR, and a couple different DR systems, so have observed a great deal. Various manufacturers accomplish the same task differently and don't always publish on the web their methods of how their systems work. Let's take a look at how collimation can affect a digital image. An example of how a computer might find an image on a DR imaging plate can be by pixel analysis and can use the histogram to find the image pixels. Here is a lateral skull image that is properly positioned and tightly collimated, captured on a 14 by 17" imaging plate. A histogram is generated for the image. Note that there is a sharp, tall peak on the right side of the graph. The height of the peak indicated many white pixels, and the width indicates not much density variation for these pixels. These pixels represent mostly the unexposed pixels that exist outside of a collimated image. Most properly exposed radiographs have a black border surrounding the anatomy. These pixels are exposed to radiation with nothing but air between the X-ray tube and the imaging plate. These pixels have more density variation, so the peak is thicker horizontally. Pixels in the middle of the histogram mostly represent soft tissue and bony structures. To find the image, the computer looks for unexposed pixels adjacent to border pixels and determines the borders for the image. Notice the proper use of the collimator plays a significant role in this determination. Pixels outside the border area are excluded from the image. Pixels inside the border area are included and sent for correction, display, and storage. Below is an example of how collimation might affect the histogram and image quality. This represents a lateral skull with good collimation, and to the right is a histogram that represents the image. Notice the span of useful densities. Here is the same skull demonstrating poor collimation, and to the right its histogram. Note that the span of useful densities is smaller, and more of the histogram is devoted to black pixels, which image would be more accurately reconstructed when the computer analyzes the image. Hopefully your answer is the first. There is a professional and ethical question also to be considered with a poorly collimated lateral skull. The image is not properly corrected by the computer because the number of black pixels is way off because of poor collimation. A larger than necessary tissue volume is exposed to the primary beam, meaning that the patient received a larger than necessary radiation dose for that image. Additionally, the patient produces more scatter radiation in the X-ray room. Finally, there is a matter of the thyroid gland being exposed to primary radiation. The thyroid is a particularly radiosensitive organ. The problem with misprocessing may be corrected by cropping the image and reprocessing the result. When you recrop an image, you're telling the computer these pixels are the ones I want included in the final image, and to use these pixels for image correction. Additionally, cropping can hide the radiographer's lack of care when collimating. I would recommend for medical legal reasons that you note any cropping modifications made to the captured image on the notes for the examination. Noting changes will forego any suspicion that you're reprocessing the image to hide a mistake. As for the unnecessary tissue involvement and the thyroid exposure, it is damage done. It cannot be corrected for this patient. Competent radiographers do make mistakes, but they learn from them and strive not to repeat them. I hope you can forgive my digression regarding collimation. Collimation is the second most effective thing a radiographer can do to protect the patient from unnecessary exposure, and you should always strive to collimate accurately. Thank you for your kind attention. Goodbye.